Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hi, it's Mr. T, and today I have a tutorial on exponential functions. And in particular, we're going to be looking at something called exponential growth and decay. Exponential functions are probably my favorite function. You'll see a lot of the applications that we're going to be working on involve money and planning for money. So let's get into what exponential functions are. So if we look at a problem, the way that we know that something isn't going to be an exponential function is that as x or time progresses, the value of something is being repeatedly multiplied. So we're going to be using this general model for our exponential function. So we have a constant or a coefficient here called a, and then we're going to have some number raised to the x power. So remember, if we had a times b to the first, that means a times b. A times b to the second, meaning x is 2, that's a times b, so we multiplied by b again. If we had ab to the third power, we would be multiplying by b 3 times. So anytime we're repeatedly multiplying, that's going to be an exponential function application. The number that we're repeatedly multiplying by in this model is the b. If that number, b here, is bigger than 1, then each time we multiply a number by something bigger than 1, it will increase in value. So when the value of b is bigger than 1, we have something called exponential growth. If b is a fraction or a decimal, something smaller than 1, so if you multiply a number by something smaller than 1, say 1, like 1/2, the value gets smaller. So if we first multiply a by 1/2, we're going to have half of a. If we multiply by half again, now we're going to have a fourth of a. If we multiply by half again, we have an eighth of a. So the value will decrease, and that's called exponential decay. As I said, there's lots of different applications. So some applications that you can maybe relate to for exponential growth. So planning monetarily for the future. The cost of things over time increase. You've probably heard of this term. It's called inflation. So if you look at, say, what the cost of gasoline was back when I first started driving, it was like 25 cents a gallon. And now it's almost $4 a gallon. So the price has increased. Your parents have probably been concerned about the cost of health care and health insurance. Those costs have increased over time, as well as like college education. So that's called inflation, and we can use exponential functions to predict what the cost of something will be in the future. As you get a job, hopefully your wages will increase. Hopefully you'll get some kind of raise each year. So if we want to predict what our income will be in, say, 10 or 20 years, we could use an exponential function for predicting that. Investments, especially if you say you're planning for your retirement or saving for a house, investments grow every year, hopefully, on average by some percent. So that's also exponential growth. And in the sciences, things like in medicine, things like bacteria, viruses, those cells split and the number of the cells grow repeatedly over time. So we use exponential models for modeling things like population growths of various items. Sometimes things decrease in value, and one particular one you can maybe understand is the value of a car. If you buy a new car, as soon as you drive it off the lot, it's worth less money, and every year it's worth less and less. So that's called depreciation, and we'll use exponential decay models for that. And finally, some of you have heard about radioactive decay, and maybe in archaeology we find, say, fossils and artifacts, and we want to know how old they are, and we use something called carbon-14 dating. Well, the isotopes in carbon decay, and the rate at which they decay is an exponential model. So you can see this particular function has lots of real-world applications. That's why I like it. When x is 0, that's what's referred to as our initial value. So when we look at applications and are trying to write this model for a problem, for a word problem, we'll look at what the initial value was, and that will be the value that we use for A. B is our repeated multiplying factor, our growth or decay factor. So in the words of the problem, there may be things like something doubles every year. Doubles would mean we're multiplying by 2, so B would be 2. Or it may say something cuts in half, so we would be multiplying by 1/2. For percent increases or decreases, we need to come up with multiplication factors. And you should remember from pre-algebra and algebra 1, if you want to increase something by 5%, you multiply it by the 5% converted to decimal, 0.05, but you have to add it to 1. So if you multiply something by 1.05, you are increasing it by 5%. If we wanted to increase by, say, 10%, we would multiply by 1 plus 0.1, which would be 1.1. To do a percent decrease, we subtract our percent from 1, or subtract from 100%. So if I want to do a 20% decrease, I would multiply by 0.8. So you remember, again, if it's an exponential growth, our B value will be 1 plus the percent. And if it's, so for exponential growth, B will equal 1 plus the interest, or the percent rate as a decimal. And if it's decay, our B value will be 1 minus our rate. So let's look at this model. Now in this model, is this exponential growth or decay? So again, we look at, this is our B and this is our A. So since this number is bigger than 1, this is exponential growth, meaning it's increasing. Now remember, the initial value for y is the A, so the initial value of y would be 350. And since this was growth, to get the percent, we did 1 plus the percent, the rate. So 1.035 would be 1 plus 0.035. And that as a percent is 3.5%. So this model is representing 3.5% growth. And lastly, if we wanted to find the value of y when 12, we would just plug 12 in for x, and we'll use a calculator. So I'll bring the calculator here over in a minute and show how we would enter that. So let's turn on our calculator. So we're going to enter 350. Parentheses for our b, put in our b value, 1.035. Close our parentheses. Remember, we use this caret key for our exponent, and our exponent is 12. And we get this number, and we would just round it. Depending on the problem, we would round it to either a whole number or a decimal. Let's round this to, say, 2 decimal places. So it's increasing because our initial value was 350, and after 12 growths, it's up to 528. Let's look at a decay problem. Now this is our B, and 0.875 is smaller than 1, so this is decay. Our initial value is this number here, so our initial value is 925. Now to find this percent for decay, B is 1 minus our rate. So we've got 0.875 as our B is 1 minus something. So I need to know what number would I subtract from 1 to get 0.875. So that would be 0.125. So 0.875 would represent this rate as a decimal, and that is 12.5%, and it would be a decrease or a decay. So this model represents an annual or every interval a 12.5% decrease. Now again, we can plug in 10 for x and do a calculation. So let's calculate that. So we've got 925 times 0.875 raised to the 10th power. So we're just using a calculator here, and we would get for this 243.34 if I rounded to 2 decimal places. Now in these cases, we were given the exponential model and we're just trying to interpret what it meant. So now let's look at a couple applications. So here's our first application, population growth. And we're going to do two things. We're going to write a model, meaning we're going to write a function for this problem, and then we'll use that model to answer a particular question. Now I'm going to use function notation here, and since we're talking about population, I'm going to use the letter P for our function. Remember, that just means y. And our model we're using is y equals a b to the x power. So y is our p of t. And remember, a is our initial value. So our initial population for this problem is given here. So 43,230. And now this is a growth thing because we're growing at 3.5% per year. So our rate is 0.035. And remember, when we want to create a b value, we have to add 1 to that. So our b value would be 1.035. And t, our x, is going to be our years since 2000. So that would be the model. So if we wanted to find the population in 2015, that's 15 years after 2000. So t is 15. So we just use our model here. So 43,230 times 1.035 raised to the 15th power. And since we're talking about people, we'll round it to say the nearest whole person. So our estimate of the population in 2015 would be 72,425 people. Now that's an estimate because populations in towns don't grow at the exact same rate every year. But as a predictor, looking at this historical data, we're growing at that rate. So if we assume that growth rate continues, this would be our population in 2015. Okay, let's look at a car purchase. Again, the value of cars decrease. Now, through research and stuff, you can find information about how different models decrease in value. Some models decrease at a fairly rapid rate. Some models that are very reliable and have a lot of interest from buyers, the decrease in rate might not be as much. So I picked a typical value. So again, our model, this time we're going to use V for value of the car. Now we need our A, which is our initial amount. So our purchase price was our initial value. And now we need our B value. Now this is a decrease by 15%. So our rate is 0.15. But our B value, since it's a decay problem, will be 1 minus 0.15, which is going to be 0.85. So 0.85. And our time is number of years we've owned the car. So this would be the model. The model will always have a letter in for our X. And now we can use the model. So at 6 years, we could calculate. So we're going to use this model, 33,599 times our B value, 0.85. And we're going to raise that to the 6th power for 6 years. And so our car value will be about $12,000, 671.85 cents. So you can see after a few number of years, the car's value has decreased rapidly. Now this one's similar, but it's a little different because when we get into it, you'll see that the model's a little bit more complicated. So bacteria or different kind of cells usually grow by doubling. The cells split every certain amount of time. So in our growth model, our initial amount is the 10,000 cells. And our growth factor, we're doubling, so we're multiplying by 2. But when we do our exponent, it's not going to be h for the number of hours because we're not doubling every hour. We're doubling every 5 hours. So to find out how many times we've doubled, we've got to take the total number of hours and divide it by 5. So our model might be t for the number of hours divided by 5. So this would be our model. So the complexity when we don't grow every single hour or every single year or day, whatever our time unit is, we have to divide our exponent to figure out how many times we've grown or decayed. So now to get in 24 hours, we're going to have 10,000 times 2 to the 24 fifths. Now that's going to end up being a decimal number, but that doesn't matter. We can still figure out our answer. So 10,000 times 2 to the, now I've got to put this in parentheses, 24 divided by 5. So if your exponent is some calculation, you need to put it in parentheses. And we have here 278,576 cells. So that's going to be after 24 hours. We've not quite doubled 5 times. We've almost doubled 5 times. We've doubled slightly less than 5 times. Now to wrap up, we're going to talk about one final application here, but to do that we have to talk about this number e. Now there's some special numbers in math. The one that you're familiar with is pi. We've used that when we deal with circles and when we deal with trigonometry. This is an irrational number. It's approximately 3.14. But remember, irrational numbers continue forever. We'll be talking about this number when we come up on Pi Day. We've used I to represent a number. That's been the, remember, the square root of -1. And now we're going to have a number called E. It's referred to, the natural number is one name for it because it's used to model lots of natural phenomena. It was also given the letter E by its discoverer, or in recognition of its discoverer. A mathematician named Euler discovered this constant. He used some calculus and looked at a model here as n keeps, in these two places, keeps getting bigger and bigger. He realized that this computation kept approaching a particular constant, E, and again, it's an irrational number. There's other videos that you can look at that go into a great more depth about this number. I just want here, what's important is we just know it's a number. And it gets used in exponential growth for something called continuous growth. Continuous growth, what you can think of it as something that's growing every instant in time, every millisecond, every second of the day, every millisecond of the day, it's continually growing. And one type of growth we're going to look at is dealing with money. Now in banking terms, we use something called compound interest. When you see the word compound, what that means is that you put money into, say, an account, an investment account or a bank account, and periodically they're paying you money to hold your money for you. They're paying you interest. And when we're compounding, we put that money they pay you back into the bank account. And the next time they pay you interest, you're getting interest not only on your original balance, but on the accumulated interest. So the amount of interest we get the second time is going to be a little bit more because we're getting paid interest on top of our interest. That's called compounding. You studied one model for compound interest in Algebra 1, and we're going to talk about a different model of that called continuous. So you can continuously compounded interest, as we're going to be talking about here. So what you can think about is the money in the account as every second is growing by a little bit. Now the model to predict the value of an account, we use this model here, the PERT model. And let's talk about what the terms are. Some of these terms we're using banking terminology. So this P comes from the word principal, which in banking is the amount of money that you initial deposit. So our initial deposit is P. It's going to go here. It'll be a number. E is a number. It's a constant. It's the natural number. R will be the interest rate that we're being paid on our investment, or that we're earning on our investment in decimal, and T will be the number of years. A will be the amount of money in the balance or in the account after T number of years. So let's look at here. Let's say we inherited some money and we're going to save it to buy a condo maybe in 6 years after we graduate from college, or at least put it as a down payment. So we want to figure out how much money we're going to have in 6 years, and we're paid 5% compounded continuously. So when you see the words compounded continuously, that needs to trigger that you're using the model, our PERT model. And we want to know in 6 years, so we need to know our initial deposit, which is going to be our inheritance. We're not going to spend that. We're going to put it in the bank. We're going to be responsible. E is the natural number, and then our exponent is going to be 5% as a rate, which would be 0.05 times T. That would be our model, and we want to know for 6 years, so we're going to put 6 in for T. Whoops, that's going to be a 6 now. So now we can bring the calculator. Now to get the E raised to a power, we don't want to type in the decimal approximate. So if you right here above the natural log on the Texas Instrument graphing calculator, we can get an E to a power. So I'm going to be pressing the second button to get that. So I'm going to enter my 10,000. And now I need to get my E to the X power. So second, and then the LN button, I have E to a power, and then we're going to put in 0.05 times 6 years. So after 6 years, our inheritance that we're investing is now going to be worth $13,000, $498 and about 59 cents. Now, what if we decided to leave that money in and just forget about it and leave it there for like 30 years, say for retirement or our kid's wedding or a big trip or something like that? So what happens if we put this in for 30 years? Let's look at what happens. So let's go back and edit this thing, and let's change our 6 to 30 years. And we've got $44,000. So after 30 years, we've got $44,000, about $44,817. So you can see the money, if you just let it compound, it keeps growing faster and faster. So that's our exponential growth and decay models. And good luck with completing your notes assignment and your practice exercises.
Are you ready? Are you ready? Oh, oh.